No, it's recording. Right, let me. Yeah, that's good. Okay, so basically, some of you have seen this. I put it on the. I put in Canvas. I have here some hard copies. If you are in class, otherwise, if you are just watching, you can just print it from Canvas. So basically what I try to do is something similar to what we have done so far in class, and try to put some, make it a little bit more spicy if you want. Okay? So basically remember we kind of discussed about this problem, same as the homework, but this time we replace those bars with strings, no? So instead of just having that x double dot term, we'll have some kx term. All right? So again, doing my Newton and Lagrange method, I think that you should be able to handle it pretty easily, no? Given that is similar to the homework problem. Now, this one, if you follow the same steps as before, you should be able to get it. It's kind of something similar. Okay, find the equation of motion. Once you find the equation of motion, you can determine what is the natural frequency, no? Okay, everything's symbolic so far. Then I want to do a little bit more applied. So this time, kind of the same problem as before, but what did I do this time? I added a damper. Okay? So basically, you still need to find the natural frequency, but what I kind of did over here is that, knowing that the natural frequency of the above system is 10 Hertz, so this is vibrating at 10 Hertz, and that the amplitude of vibration is reduced by 60% in 10 cycles, determine the stiffness and the damping coefficient. So basically, remember, you should be able to determine the damping coefficient from the response, no? Mm-hmm. Okay? And then if you know the frequency, what is the frequency is k over n, you know the mass, you should be able to determine k. All right? A little bit of an inverse problem. You find the equation of motion, you find the solution, and once you have the solution, you kind of work it backwards, okay, to find what you need. And the last one is something kind of similar. Is this time the only thing I did was, let's say there's a car that moves of certain mass going with certain velocity, and you have some type of stopper over there at the end. So what should be the values for K1 and K2 if you have some, let's say, design requirement? Let's say these can only move about 20 centimeters, and that you want the impact to be absorbed within half a second. Okay? So I tried to do a little bit more practical on the last two problems. So 2, just to go through the basic that we have done. 2, a little bit more applied. Mm-hmm. Okay? All right, so let's go for the big theoretical part today. So remember yesterday, we did the, so let me go to the notes over here. We did the damp vibrations, okay? So we found the type of response of this form with the H, which is then called the transfer function. We went through a bunch of algebra, so on, so on, so on. Then we got to this figure that I said was important to know the understanding of this figure, okay? And after that, we had a small discussion saying that the solution, that generally the solution will have two parts. One, the homogeneous, that will be the solution to the problem here where the right-hand side is 0, plus the particular, where you will have the value on the right-hand side. So this one is non-homogeneous, not the particular solution. Okay? So let's do one example. Oh, this is the exam, I'll just keep it there. So let's get started. All right. Now that I got new markers, I need to put that page at the back because otherwise it's going to mark the page behind. Let's see what was the last page we did yesterday on the notes. 40, looks like it is. All right, there we go. Okay, before we start, so the exam is due next Wednesday, so you have plenty of time, and you need to submit it online. So I'll let you submit PDF files, MATLAB files, and then also put at the end Maple files. You want to do some of the algebra in Maple to check your algebra, you can do it, okay? All right, so there we go. So let's do here example. All right, so let's say that we have a block over here of mass M, which is attached to a spring and also has here a damper. K and C, and this is subjected to a force F of t. Well, F of t, this time we're going to solve this in trigonometric notation, so let's put it here, trigonometric notation. Will be A sub naught cosine omega t plus B naught sine capital omega t. So what is capital omega t? What is the difference between capital omega t and omega sub n?
It's the capital omega is the frequency of the forcing function instead of the natural frequency of the system.
Perfect. Okay, don't confuse both of them. So we assume here no friction. All right. So let's do the procedure. One, we need to do some type of sketch or diagram. Okay, remember that all the equations do not show up magically. They need to come from some type of figure or sketch. So I'll start going a bit faster. By now, you should know this. The force of the spring, force of the damper, F of t, and this will be mx of it. Okay, so now we applied Newton's equation on the x direction. Give us what? Minus kx minus cx dot plus f of t equal mx double dot, which will give us over here mx double dot plus cx dot plus kx equal to f of t. Okay, so 3 solution. So we can say over here, the solution of the above equation is of the form x of t equals x of h of t plus x sub t of t. Where yesterday we already discussed, this is the homogeneous problem. The homogeneous solution, which corresponds to the problem mx double dot plus cx dot plus kx equal to 0. This is the particular solution, which corresponds to the problem mx double dot plus cx dot plus kx equal to f of t. Okay? Okay, so the first part is going to be pretty quick because I'm not going to redo the whole derivations. So first thing we're going to look at is at the homogeneous solution. Okay, so for the homogeneous solution, we had three different cases that were what? Let's see if you remember, we had the damping ratio to be higher than 1, damping ratio equal to 0, damping ratio lower than 1. So what was the name for this one?
Overdamped.
This one is overdamped. This one is when we had the two roots equal one to the other, no?
Mm-hmm.
Which is called the critically damped. And this one is the underdamped. Okay, so I'm not gonna space over here, but let's do over here for, let's call this A, B, and C. So after doing the calculations, after we have the data, okay, what is the solution for the homogeneous solution if the system is overdamped? Remember the general form was C exponential of minus damping plus square root of damping square minus 1.
Close parentheses times omega n t.
Correct, omega and t.
And
Plus C2 over here, exponential this time of positive of the same thing here, minus, but this one is minus here. omega nt. Maybe I should change the color over here. So if the system is overdamped, this will be your X homogeneous. Then I'm going to change the color. If it is critically damped, what was the response? Exponential of minus omega t. Remember when you have two repetitive roots, what do?
C1 plus C2t.
Correct. So you need to multiply the 1 by t. So this would be for the critically damped. And if the system is underdamped, we still have the exponential of minus xe omega t times C1 exponential of minus the damped frequency plus C2 exponential of omega t. Oh, I forgot something here. I forgot the I. We have an I on this one. Okay, so now that we have the homogeneous solution, this will be xh of t. That we need to solve for is what? The particular solution. And then just call it xp of t. Okay, so remember the equations we have. We need to solve the equation mx double dot plus cx dot plus kx is equal to f of t. Or this, in our case, becomes what? Mx double dot plus cx dot plus kx. Let's say this would be x sub p, x dot sub p, x dot sub p. Will be equal to what? What is f of t? What's equal to, let's look at the first page.
It was A naught cosine of
All right, cosine
capital omega t
omega t.
plus B naught sine of capital omega t.
Omega t. Okay, so do you remember the procedure to solve the differential equations? What do we need to do? What is the first thing to do?
Assume the solution point.
Assume the solution. And before we assume the solution to be of
Harmonic.
an harmonic function. But then when we saw it yesterday, we kind of assume the solution to be
Of the form
of the same
of T.
form as the exciting force, no? Or the forcing force.
Mm-hmm.
So we can say over here, assume our particular solution, let's say xp of t, to be equal to capital A sub p cosine omega t plus b p sine omega t. All right, so now what do we need to do with this x? We need to differentiate once for the damping
And differentiate a second time.
and differentiate a second time for the mass. Then we're going to substitute into this equation We're going to equate this side to this side, all right? And then how do we solve for the values of a sub p and b sub p? We do equate the coefficients that will be in front of the cosine and sine function, okay? And that will be it. So basically, what is the general form of the solution? Is AP cosine BP sine. So this omega here will be given to us in most of the prime because it's part of the forcing function. A sub naught, B sub naught will be given. The forcing function is known. What we need to find is the two constants, A sub P and B sub P. Okay, so this is basically something I think you have done in differential equations, but it doesn't matter. We're still going to go in detail at least once, but no more than once. Okay, so page 43. All right, so what do we have over here? We take xp of t equal AP cosine capital omega t. I'm just writing the same equation to have everything on the same page. Okay, so what will be x dot of p?
Negative AP, negative AP omega
Yeah.
sine of omega t
All right, perfect.
plus BP omega cosine of omega t.
Okay, perfect. We do the same thing for the second derivative. So what are we going to get this time?
Minus AP omega squared cosine omega t
Mm-hmm.
minus BP omega squared sine omega t.
Okay, so now we substitute into, I'm going to put here the short form. Okay, I'm not going to write everything again. So what are we going to get? We're going to get, let's see, I have to start writing here, m of x double dot, which is minus AP omega squared cosine omega squared t minus BP omega squared sine omega t. I'm not going to try to write everything on one line. Let me just do plus over here. What will be the next term? C of x dot. So all this term over here is the x of a dot. One is C dot is minus AP omega sine capital omega t plus BP omega cosine omega t. Forgot to close the bracket here. All this term will be x dot. We have k over here, and k will be AP cosine capital omega t plus BP sine capital omega t. Okay, and all this should be equal to what?
The f of t function.
A sub naught, yeah, cosine omega t plus b sub naught sine omega t, which is f of t. Okay? Okay, so now what is the idea? What do we have on the right hand side? We have cosine and sine, no? And we have here a coefficient. So what we try to do now is to put here all the coefficients of cosines together to be able to equate to this one, all the coefficients of the sine together on this side, no? So let's see what we get. So this will give us, so rearranging. So let's see, what I'm trying to get is cosine omega t. What would be the terms? So there we go, would be, so let's start by the first one, minus m a sub p capital omega squared for the first term. Then what do we have for the second term?
Minus c a sub p omega.
No, we have the BP, this one, no?
Oh,
That's right.
So plus C BP omega. And then for the last one will be plus AP.
KAP.
KAP, correct. All right, next we have here would be the same thing for the sine, capital omega t. So the first term will be minus m bp omega squared minus c ap omega plus k bp equal to a sub naught cosine omega t plus b sub naught sine omega t. Okay, so now what is the idea? Is to equate those coefficients, this long one to this one, no? Both are in cosine omega t, and the sine to this one. So let's say over here, equating coefficients for cosine omega t and sine omega t. what do we have? So I'm looking here at the page, on top, let's see if I can do it this way. So we have minus m AP omega squared plus c BP omega plus k AP to be equal to a sub naught, and minus m BP omega squared minus c AP omega plus k BP equals to b naught. Okay. So now we need to solve in for, what do we need to solve over here for?
AP and BP?
Correct, the particular solution, so A sub P and B sub P. There's one thing, it's not on the class notes, so maybe we can do it together now. I have the results in function, the values of A sub P and B sub P in function of omega sub n, which is k omega. But let's do the middle step. For that, let's just use Maple. That way you have a sample file for Maple as well. So home, let's go to computer. Let's see if we can do that. Delete. Have we used Maple in this class or not yet?
A bit.
We did, and I give you a file? Oh,
think so,
yeah. Maybe, this is strange, I don't need to do this, so this is like in MATLAB, clear all CLC, okay? We start. Try to do it bigger. I don't even see it myself. Fine. Restart. Basically, let's just say first equation. What is the first equation? Minus m times AP times omega
Flashing.
square
Flashing.
plus c times BP times omega plus k times AP minus a, so we can write it this way, I guess. Oops. What happened here? And then this. That looks right. And maybe I can do this. There's not much to change. what is equation 2 is minus BP omega square minus C BP omega
Shouldn't that be
plus K BP. Is that correct?
AP? KVP, but I think it should be CAP there.
In the middle.
This one?
Yeah.
Yeah. CP.
And at the end it should be a B naught. The next one, that one.
Yeah. There we go, there we go, there we go. So I don't know why this is not becoming bigger. And then you type solve. Equation 1, hopefully it will work. Equation 2. I'm going to solve for A sub P, B sub P. Oh, this time it did it. I remember, I cannot remember. I think last time we had a little issue, no?
Yeah, I think so.
All right, so it gives you this expression for A sub P and B sub P. And now we can write them down. The thing is that I put the monitor. Okay, so you write it down as I do it. So solving for A sub P, B sub P, we get A sub P equals to minus, I'm going to be a lot faster than me, and A sub naught omega square plus C B sub naught omega minus K A sub naught divided by M squared capital omega square plus C squared capital omega square minus 2 and K omega square plus K square. BP equal to minus and 0 omega square minus C A0 omega minus K B naught. Okay. Oh, there's a mistake. It's 2 4. Alright, so we need to down to cut camera. So I just copy those values. Okay, so to save some time, I'm not going to do the bits over here, but I'm going to write down using the fact that omega n squared equals to K over M. A sub P and B sub P become what? So let's see, I have the expression here. So A sub P becomes M A sub naught omega n squared minus capital omega square minus B sub naught C omega divided by m squared. I don't know why I didn't simplify. Omega n squared minus omega squared squared plus C omega squared and dp will be equal to m b sub naught omega n squared minus capital omega squared plus a sub naught c omega divided by the same thing. Okay, so finally, the particular solution x of p of t is obtained by substituting a sub p and b sub p into AP cosine capital omega t plus b sub p sine capital omega t, which obviously I'm not going to do, okay? Okay, so here we can say final solution, so final solution is what? Is x of t equal to x homogeneous of t plus x of p of t. Okay, so let's go back here to those notes. Oh, there is the page that I'm looking for. Right here. All right, so what would be the solution? Let's say the system is on the dam. You will use this part of the homogeneous solution, correct? Plus this form of the particular solution. Do we have any unknown in this equation? AP will be known, BP will be known. Okay? The forcing frequency is known. In the homogeneous solution, will something be unknown? C1 and C2, no? So from where do you need to solve for C1 and C2?
The initial conditions.
From the initial conditions. Perfect. So if you want, make a letter note here. Solve for C1 and C2 from the homogeneous solution from initial conditions. Okay, here be careful because maybe the arrow can be confusing. When you solve for the initial conditions, you need to consider the full solution, no? Not only this one. So let's say they give you the displacement, would be the displacement of all these expressions. And if you find the velocity, we'll have the velocity of all these expressions. Okay? So here we went through the procedure using the algebra. How much time we have left? Half an hour?
45 minutes.
Oh, we have one. Okay, 45 minutes. So let's try to do an example. We're gonna go faster. I know this is pretty tedious, but I think you need to at least see it once, no?
Yeah, I think so.
Yes. 21, so I think that's what we did so far. This is the one on the page that I put at the back, because the marker goes through. All right, so page 45. All right, so let's go a little bit faster here. There will be an exercise. So for the data, M equals 5 kilograms, K equals 10 Newton meters, and C equals 1 Newton per second meter. So we have this system over here, this system that we always have. Okay, see. F of t, where f of t is equal to 10 cosine 5t. It's a little bit different than what I have here on the class notes. And we're going to apply here the initial conditions. So at t equals 0, x is equal to, oh. Here I have 0 and 0. That's pretty strange. You can change it, huh? But let's use 0 because let's just use the ones that I have over here. Because that way I can check. Okay, so I'm going to go a little bit fast over here. First thing to do will be to find the equation of motion. So I guess this little diagram, you know it by now, no? Okay, x, Cx dot, f of t, mx of it. One, this will be step 1, diagram. Step 2, Newton's equation. down, summation of forces equals to MA on the x direction. And we get the equation, I'm going to go a bit faster, mx double dot plus cx dot plus kx equal to above. Okay, to go a bit faster, we're going to change that the way it is on the class notes that you will have, the set of class notes. First thing will be 5. We're going a bit faster, but it still is for the procedure. So 3 will be solution. So what do we write down over here? The general solution. Solution is of the form x homogeneous t plus x particular t. Okay, so first we're going to look at what? At the homogeneous solution. Alright, so I guess here let's try to put some values. What is omega sub n of the system? Is k over m, which in our prime would be what?
Square root of 2.
Yeah. Square root of 2 radians per second. Now, go back to the notes. How would we determine the damping ratio exceed? What was the expression? It was
C over 2m omega n.
C over 2m omega n is equal to damping ratio? Okay. So the damping ratio is equal to what in our problem? Is 1, no? Divided by 2 times 5 times square root of 2. I need to go to the next page. Or what is this value? I don't have the result, so I'm doing it differently. I'm trying to go a bit faster. So.
.0707.
1,
No, the .0707.
0.07.
Yeah.
So basically what am I doing that? Is to see what is type of response we have, no? So We are in the case that is lower than 1. So what type of response is that? Underdamped. And if it is underdamped, that means that x of h, what was the general form of that? Was exponential of minus damping ratio omega n t?
Mhm.
Yes?
Yes.
I mean, I'm doing all by memory here, so I don't have the equation. And this should be now c bar 1,
E to the negative I omega dt.
that is I, okay. And here will be the uh, 1 minus damping ratio square, no?
Mhm.
Mhm.
Omega n t, another space, plus C2 exponential, this time of the positive I, 1 minus xc squared omega n t. Okay, here I'm going to put a note, important, so what is this sign? Did you pass the driving license?
Yeah, caution, warning.
Caution, warning, attention, okay? So, solve for C bar 1 and C2 at the end of the, I mean, doesn't make sense of the problem, but what I want to say is that basically what I want to say is when you have the total solution x equal x homogeneous plus x of p. Okay, don't solve it now. All right, now we go to the particular solution. Okay, so what do we need to do for the particular solution?
Find AP and BP.
Correct, but I mean, we need to assume the particular solution, no?
Mm-hmm.
So particular solution, we say was of the form of what? X of p, a sub p, what was before cosine, no?
Mm-hmm.
So cosine omega t plus bp sine omega t. In this problem, what is capital omega for us?
5.
5. Okay? Okay, let's do it here once. Open space. X dot p is what? Minus
5
AP lambda sine omega t plus bp lambda cosine omega t double dot p will be equal to minus AP omega squared cosine omega t minus BP omega squared sine omega t. Okay, so let's use some of the data here because, all right, so substitute into what? Mx double dot plus Cx dot plus Kx equal to, what is in this case equal to 10
10 cosine of 5t.
cosine of 5t. Okay, so I'm going to start putting values over here, okay? It's going to be easier. So we know that capital omega equal 5, n equal to 5, c equal to 1, k equal to 10. All right, so maybe I change colors so I don't do clear here. All right, so the first one will be what? M is equal to 5. So it will be equal to 5 times x double dot, the particular solution. So that will be minus AP omega squared, oops, sorry. Can I just put the, right. I'm going to put the value, so this should be equal to what? 5. So we do the xp first, so we do the cosine, so I'm not doing that, so we'll be next, so we do, sorry, 5, so it will be what? Omega squared will be 25, no?
Mm-hmm.
Minus 25 a sub p cosine 5t
Minus 25 BP
minus 25 bp
sine of 5t.
sine of 5t. Plus, now we do the other term, c is equal to 1 of x dot would be minus 5, no, yeah, minus 5 AP sine 5t plus 5 BP cosine 5t plus the kx, so k is 10, so x is AP cosine 5t plus BP sine 5t, and all this is equal to what? 10 cosine 5t. Okay, what should be the next step?
Set the coefficients equal to each other.
Set the coefficient, oh yeah, but we first need to set all the coefficients in front of the cosine, put them together, same thing for the sine, so that then we can equate the coefficients, no?
Mm-hmm.
So one more step, so this was page, I'm losing track, so 46. A lot of writing today. So So if I rewrite this, we'll have, so rearranging, what are we gonna have? So cosine 5t, we can factor that one by what? Minus 125 AP,
Why is it 125?
5 times 25.
Okay.
Then we have plus 5 BP. And the last one will be plus
Plus 10 AP.
plus 10. Plus, we do the same thing for the signs. So what would that give us for the signs? Minus 125
BP.
BP.
Minus 5 AP.
Minus 5 BP.
And plus 10 BP.
Plus 10. Good. And all this should be equal to 10 cosine 5t. So we do equating coefficients. What do we get? Minus 124. Maybe we can add them together. So minus, sorry. How many BPs we have? Minus 115 AP plus 5 BP will be equal to what?
10.
10. This 10 over here. And the one will be minus 5 AP
Minus 115 BP.
minus BP.
Is equal
And
to
this one should be
0.
equal to
0.
0 because there's no sign. Okay, so now that we have this, what do we do?
Solve for AP and BP.
Solve for AP and BP. I mean, 115 divided by 5 should be
23.
23. So we could multiply this one by 23 and subtract, no?
Mhm.
But then we have 23 times 115. So it should be pretty small values. So BP will be pretty small.
Yeah, it is.
Mhm.
Do you have a value?
0.003.
Okay, so BP, can you give me more decimal?
0.0037773.
So 38.
Yeah.
Okay. Then give me 2 decimals and AP.
0.08679.
0.0
8679.
867. 867. So 8. I put the same decimal. So 8, 6,
6, 8.
8?
To round, yeah.
So we have the same number this one. Is one of them negative?
I got them both. as-
Because this one should be negative. You see here?
Mhm.
Looks like someone is going to be negative in this one.
Oh,
Not both positive? They can be both positive, I don't know. No, this is not way positive
Wait, hold
because
on,
this
I
one
must
will
have
not give
negative.
0, no?
this might be different. Give me a second.
You see this one? In this one, they can both be positive, negative, but the second one, you need to have a change in sign, no?
Yep.
Hold on a second.
I mean, I'm gonna have the result for this. Ah, it is. You have 0.0038 for BP, okay? AP, I think, is negative.
Okay.
But if you want to check, I think the one is negative.
Yeah, 80 would be negative.
AP would be negative, perfect. So, okay, so the particular solution becomes x of p equal, let me just write it, was a sub p cosine omega t plus bp sine omega t. So it becomes what? X of p t becomes negative 0.0868 cosine 5t plus 0.0038 sine 5t. .48, so here you see over here, the final solution is what? The homogeneous plus the particular solution. So what was the homogeneous solution? I think I can remember, but so would be, all right, maybe you need to give me, all right. I have the general solution here, my exponential of minus damping ratio omega and t, C1 exponential of minus 1 minus xc over the I omega and t plus C2 exponential of I 1 minus xc squared omega and t. So this is homogeneous. Plus the particular, which is equal to minus 0.0868 cosine 5t plus 0.0038 sine 5t. This is the particular solution. Or this is the homogeneous. Okay, last thing we need to do. What is the last thing we need to do?
Solve for C1 and C2.
Correct. So determine C1 and C2. From initial conditions, x equal to 0, velocity equal to 0, at t equals 0.
Mm-hmm.
Okay, so on the class notes here, I've done it by hand. So you know what? I'm not feeling like doing it by hand.
Mm-hmm.
So what would be the best option to do here?
Maple?
Maple, probably, no? So, wait, we have all these expressions from before. Do you want me to save this one or no? Just in case of file, save as, then I copy it over there. Desktop. How do you want me to call this one? APVP?
Sure.
Whatever, I mean, it's just an example for you, so save on the desktop, then I will put it on. Let me erase this now then. So it will be file, save as, exercise, what do we do? Exercise, XH, XP?
Sure.
I don't know, whatever is given it. So here we have, so maybe let's put values over here. So what do, let's do the calculations. So K, how much was equal K?
10.
10. M,
5.
5. And C?
1.
1. Right. I'll do that bigger now. Don't worry about it. Right, so I'm going to try, so we don't have to do any calculations here. So omega, we say was equal to square root of K over M. Then we have XC, hopefully that's the letter, was equal to what? 2 times M times omega n?
Mm-hmm.
Is that what it was? But it was something. That's not possible. That would make was 1 divided by
1 divided by all that, yeah.
1 divided by, oops. All right, so that's not the letter. How do you call it? C? Number.
Hold on a second.
I thought it was like that, but
Oh, how you spell it? It's XI.
so it wasn't correct.
Yes, that's all.
Yeah, the way you spell it.
So how do you spell it? Then X,
XI.
XI, that's it?
Yep.
That's it, is that right? So XI,
Well, it looks like something's going on with the calculation because omega should be in the denominator, but it's putting it as a separate term when it calculates xi.
the omega.
Yeah. You'll see omega is square root of 2, but on the xi calculation, it's 1/20th of square root of 2 instead of 1 over 20 times square root of 2, like it should be. I don't know why Maple's doing that. Maybe it'll...
Maybe they just rewrite this part, no?
Yeah, just put in parentheses, it'll probably be fine.
It's right,
So 1
That's square root of 2 is
divided by
it's one of
2
the 10
times
square root
n times omega.
Top and bottom.
Oh crap, you're right. Okay, actually it wasn't a problem, sorry.
This is the same as before, but I guess it's correct.
Yeah, it's actually right, sorry about that.
Oh, that's fine. I don't know why it's not giving a value. No idea. Okay, so now we have x, the total solution. Maybe let's do it separately. Let's do x homogeneous was equal to what? C1, no, exponential of minus psi times omega times t plus C1 times exponential of, let me look at this. I don't know what, I don't know if you use the letter I or capital I, this one. Let's use the letter one if we need to change it. Of I times square root of 1 minus xi square times omega times t. Let me close the parentheses here. See how would that show? Okay. Let me check something here again. Okay, I'm not taking the complex. Use capital I looks like. So capital I. Plus C2. I did a mistake here. No, it should be the minus on the first one. Yeah, it should be minus I. So one should be the positive I. I will introduce it. Okay, I'll make it bigger later on. The x particular was equal to what? Negative 0.0868 times cosine 5 times t plus 0.0038 times sine 5 times t. What did I do here?
You accidentally put an extra, yeah, that.
I have an extra one. All right, so x equal to x homogeneous plus x particular. Actually, it's not that bad to do a derivative of this one. Okay, so let's now let's do the velocity should be equal to what? Differential of x with respect to t, no?
Mhm.
All right, so equation, so at t equals 0, equation 1 will be equal to what? To all this stuff, no? Can I just put x? Maybe it would work. And equation 2 will be equal to this. Looks like that one. Point 2. What do we do at the end? Solve those two equations for what?
C1 and C2.
C1, C2.
The last curly brace should be a regular parenthesis.
Well, I guess. So what right now, I think there's a comma here. Why don't I go there? Ah. Now, okay? So we have C1, C2. Now that we have C1, C2, this is what I will do. C2. Okay, so now what will be the final solution? You will have to go and substitute over there, no?
Mm-hmm.
Okay, so what happens is that the t is not 0 anymore, so what can we do this? Let's do another clear all or restart. Restart. We can do a lot of copy paste now, okay? We put this over here. What else we need to copy paste? Probably these lines over here, these lines over here. And I mean, you see, you can do a lot of copy paste now on this, so. All right, does it look pretty?
Not exactly.
No, I agree with you. But personally, let me tell you something, let me say this. So what I will do, and this is small, we'll probably finish next time, but what would I do with this in order to plot it? Then I would just do this. I think you can plot it in this, but I'm not that good. I will go to MATLAB. You can almost put all the values. Actually, I think we can do it differently, but basically the thing is that I do a lot of copy paste between Maple and MATLAB.
Mm-hmm.
So let's say you could come here, and let's say new script. It's a new script. Why did I open this one at the bottom? I don't want this one. View. I just want one thing. None, not just put that.
Yep, should be fine.
I'd rather have it that way. Why did you want that? All right, so what I will do anyway is come here. Maybe I will make it a little more pretty. Maybe I will just do this to the truth. XP, oops. Let me do this. I will come over here. Clear all. Clear C. Control D, Control Z. I'm trying to select maybe too much. I will come here, do line by line. There we go. You remove the 2 points over here. You put a semicolon. You do this. Does your capital I or lowercase I? MATLAB, no idea?
Don't know.
We have to find out. Lowercase you think it is? Probably it is. So you can do this here. Okay, I know it's time, but give me a couple of minutes.
Okay.
Hopefully, get it done. Oops. Max H omega. I just want to save the file that we're gonna have to read all this stuff tomorrow. So I think it's gonna work. So this is omega plus, maybe I can do here C2 this one. We go now to the particular. That should be the easy one. Okay, we can say x equal x homogeneous plus x particular, plot t comma x, say, I can do it more pretty. What do we do for t then? T equal to what? 0, 0.1 to what? I don't know.
20?
20 seconds. Hopefully this will not give any problem with the, it might give a problem, but. So we are going on here, home? Where is the run? No run?
It's in the editor tab. Up top.
Here, that one. That one?
Oh, yeah, that could work.
Is there another one?
Otherwise, you can go to the top tab, editor, and that's where the big run button is. Editor, that one.
Ah, that's the one I was looking for. Oh, desktop. Exercise. Oops. What is not typing? How do we call this one? Exercise, I think XH, XP. The one. Save. Change folder. Here we go with the I. I think we might have to do the dot for the T's.
Oh, it's in the other equation, it's in the XH expression.
Oh, this one?
Change the i's to lowercase I. Right?
To the left of the square root.
Yeah.
And there's
And then
another one. Move up a little bit. To the right.
Okay.
There.
Okay, but I think it's still gonna give the problem with the times? No.
No. All right.
Okay, it might not be enough time, but this is not enough time because this doesn't look pretty at all, no?
No.
So maybe let's just do T 0.01 to, let's say, I don't know, 16. Okay, so basically you see at the beginning gets a time and then it's gonna get onto the form. So the homogeneous solution is gonna dump out and then it should just take the form of what? Of the cosine 5t, no?
Mm-hmm.
But it will need more time, looks like it will need more time. So anyway, we finish this one tomorrow, but at least I have those files. Okay?
Mm-hmm.
I will put them in Canvas now in case they get deleted on this computer. I don't want to have to redo this.
All right.
Okay, but you see, I'm trying to show you here how to go from MATLAB to Maple, no? It might help you a little bit. So tomorrow is Friday.
Mm-hmm.
Okay, we don't want class. I'll be here. I'm teaching a class tomorrow, but I guess we're doing good in this class, so we don't need to take